It's a great pleasure for me to be here, first time so far in Europe. So first time for me here in Latvia, in Riga particularly, and I'm so sorry because I didn't have time to learn any words in Latvian, right? I usually try to say something but on the local language, but I just arrived from the airport and I didn't have time to practice anything. So forgive me, but maybe tomorrow I can try something. At least hello, right? And my name is Edson Yanaga, just in case you're wondering. I'm a Brazilian Japanese. My grandparents are Japanese, but I'm born and raised in Brazil. So I'm not the typical Brazilian you might be thinking of, but I came from there. And also a director of developer experience at Red Hat, and my Twitter handle is @Yanaga. Just in case you want to follow me, I talk a lot about DevOps and microservices, Java, domain-driven design, and all of these subjects, which I think it's kind of interesting, particularly for enterprise developers. And today I'm going to talk about cloud-native Java with Kubernetes. Initially, I thought about this session. I intended to do just a 100% live coding session to show you a lot of different steps that we could use using the Kubernetes platform. But then I was wondering if that's that useful for developers, if you're just showing people how you should be doing the things instead of why they should be adopting the techniques or technologies that are behind that. So I decided to change that for a mix of something. We will see code, but mainly we'll see why we don't have to code that much when we have a platform that is doing many of the things that we think we have to do. So I'm also a Java champion and a Microsoft MVP. And I know it's kind of a weird combination, but we live in a weird world these days. And I'm very happy to have both titles. And particularly, Microsoft granted me the MVP award because I worked with the guys from Redmond to include the Java support on Azure. So they are still improving. But if there is any support for the Java platform on the Microsoft Azure platform, is that some people, including me, have been working with them to provide even more options for us, Java developers, to deploy our applications on different cloud computing providers. So I think Java is a very great thing because we have so many different choices of techniques and platforms to be running our applications. I think it was very important to have different cloud providers providing different options. So that's why I decided to work with them on that. And I'd like to give you a tip. I just released a book from Riley, which is Migrating to Microservice Databases. When we're talking about microservices these days, the number one questions that I always receive when I'm talking to some people is that, okay, if the best practice for microservices is to take my big old monolith and break some parts apart into microservices, but I still have a big old legacy monolithic relational database with lots of tables and columns. How do I split that data? So I decided, I didn't have an answer for that, but on the past almost 2 years, I decided to research on the subject. So I've talked to many different teams worldwide on how they are solving or solved these problems, and I've collected a set of possible solutions for you to be applying when you're trying to split the data and later integrate the data on your distributed systems, in particular your microservice architecture. If you want, Red Hat bought the royalties for the book, so if you want to check the download, if you have typed this few URL, you'll be able to download the book, but we have a bug on our website. The link on the homepage is not. There's no way to find if you just type developers.redhat.com. But just in case you open my Twitter handle @Yanaga, the first pinned tweet has the direct link to the download. And I hope you enjoy. Okay. And I always like to start my sessions with this sentence, which is not from me, but from Forbes. Now, every company is a software company. I like to say that you don't work for a bank, you work for a software company. You don't work for an industry, you work for a software company, because software is changing the world that we live. And I used to think that, that economics had everything to do about money. But after reading some books about economics, and particularly behavior economics, and I realized that economics has nothing to do with money, but has everything to do with people. We're just studying how people interact with each other to take one system from one state to another state. And people have some motivations to take a system from one state to the other. Some of these motivations can be love, can be hate, can be money, can be power. But in fact, we're always dealing with people. And software is made by people, for people. Every time we forget that, we don't have an optimal result. And if software is changing the world for the people, I think we'd better change it for the better. And some of great examples that we have on this new digital economy, this new digital way of people interacting with each other, are that the largest car transportation company in the world owns no cars, which is Uber. The largest lodging company in the world owns no real estate, which is Airbnb. The largest online retailer in the world owns no stock, which is Alibaba. And the largest content network in the world produces no content, which is Facebook. All of these companies, they have something in common, that they only exist and they are all enabled through software. I also like to introduce myself as a software craftsman. And the best definition that I have of a software craftsman is somebody who cares about what he does, or he or she does. Because we know that, some years ago, I made a decision. I decided that I would want to make the world better for the people with the result of my work, with the software I did, because I know, and we all know, how can we be miserable when using software that is not up to our expectations. So we can improve the people's lives, but we can also make them feel very, very miserable. So we always have a choice. And I believe that if we are all here trying to learn different ways to craft better software and deliver that better and faster and safely into production, then we all care about what we do. And congratulations to all of us, because I think that's the best way for us to conquer a better future, not for us, not only for us, but for our children and the people we love and the people that we still don't know. And that's why I'm so happy to be here at for the first time on this place, meeting such awesome people. And I'd like to start this conversation about this question, because many people think that it's about the jar or war, but if I create a fat jar, I'm doing microservices, right? Or not? I've seen this misconception, and this is the topic for another discussion, but usually if you have a fat jar with a flat class path or something else, or if you have a war file, or have a year or something else, doesn't depend on the technology that you're using, it's just the choice of artifact that you're producing in your deployment pipeline. So it's much more important for you to think about how are you deploying software into production than the kind of artifact that you're creating. I used to be a fat jar, in fact I still am, a great fan of fat jar deployments when your deployment pipeline imposes this choice of artifact for you. Remember the days when they had that remote servers that we had to connect through SSH or maybe upload a file through FTP, and we had to deploy this kind of application. We had to install a Tomcat, and we had to copy the configuration files, and every time we changed something, we have to change again. Is my Tomcat version on that particular customer matching the version that I'm using in my machine? It was very hard to do that. For that, we had, since we're using Maven, we always had the fat jar plugins like Maven Shade plugin or anything else. We could just pack our application, we could embed web server on that, and that was my favorite deployment option when we didn't have better deployment options for doing that. But then we came through the world of containers, and now maybe something has changed. Now maybe we can be moving container images from one point to the other, and maybe we don't want to be moving the same bits of the same application server, the same libraries over and over again. Maybe it's faster, maybe we consume less space on our repositories if we just move the business logic. So it really depends. There's no right or wrong answer to that. It really depends on how is your software deployment pipeline orchestrated. And also, again, your software pipeline depends on the kind of servers, the kind of environment, the kind of deployment. If you have everything on the cloud, if you can have everything on-premise, if you have to deploy your application into each one of your customers, it really depends on how your deployment pipeline is orchestrated. So I don't have a winner for that. But I just like to say that it's just a choice of which type of artifact you are using on your deployment pipeline, and it has nothing to do with your software architecture. It's just a matter of deployment pipeline choices. Second thing is that what I call, not just me, but what is used to be called cargo code programming, which is that belief that just because some people are using something or doing something successfully, it will be good for me too. I'll be successful using that too. I don't know how many of you are aware of this cargo code thing, but the source of this term, cargo code, remotes to the Second World War. When the Allies, they had to create, because my parents, Japanese, decided to make war on the Pacific, and the Allies, they decided to, not parents, relatives, far relatives, okay? When they decided to, because my parents were already in Brazil, and they decided to make war on the Pacific. The Allies, they needed some bases on the Pacific, and then they had some island that they didn't have, they just have some uncolonized people there, and then suddenly people start arriving with big ships, with big planes, with lots of food, medication, and gifts of all sorts of kinds, and then when the war was over, they were all gone. So they were wondering, we used to receive food, gifts, medication, and all the good stuff that they brought. Why are they gone? And then they started I thought it was, they were not doing that anymore, but it's still a thing there on some islands. They are still reproducing this, try to create some airplane lanes, and they try to create some towers, and there are some people with some flags trying to sign to the planes. So they're wondering if they do the same thing that the old people did, they will have the same results. Maybe the gods will send them the planes and the ships again with the goods and the foods that they were receiving during Second World War. But it seemed that it wasn't working because they are not receiving them. Maybe the gods are not liking what are they doing. So if we get some context, the Netflix OSS stack that we have today, that we're dealing that is such an awesome piece of software, is such a great architecture. It solved many of the Netflix problems, if not most of them, that they had in 2008 when they decided to create this kind of set of libraries and architectures, and many things have evolved since. But if you see, if you check the context about what Netflix was doing in 2008, cloud computing wasn't yet a thing. People were starting to do that, and they saw maybe for our problem, we should go for Amazon and cloud computing. Amazon was the only big provider by the time, and they had a set of problems because they decided to do a distributed architecture with problems that there weren't, which knowledge wasn't widespread as it is today. It used to be I took a distributed systems, my master's degree was on a distributed systems field. So many of the problems that we tackled 20 years ago, now they're starting to become widespread. But imagine, 2008, very few people were handling that. So Netflix, they didn't have anything ready for them to be solving this kind of problems. That's why it's created this awesome stack based on circuit breakers such as Hystrix, as with smart routers as Zoo and Eureka and Ribbon, client-side load balancing. They needed a service broker, so they created Eureka, and they needed some platform for bootstrapping, so they create their own by themselves. But we are in 2017. Many things have changed from there. And the question is that, should we be just trying to do and reuse the same things that people used to be doing in almost 10 years ago? And 90% of the programmers worldwide are enterprise software developers. That's where most of us are working on, and that's where most of the money is being spent on. Most enterprise software companies in the world, they don't have the same requirements as Netflix or Amazon or Google. That's another kind of cargo code. So I always like to make people think about the choices that they make. And for many use cases, I think it's simply awesome to be using these tools. For other use cases, maybe it's not that cool to be using. Maybe you could be doing or using something else to solve the problems that we're creating for ourselves. So if you think about distributed systems and microservice architectures are a very complicated problem to be solving. There's a huge list of problems that you have to solve, but I've chosen only 5 to be discussed now because I think they're the most simple and popular at this moment to be discussing. So if you think about that microservice architecture, you have to solve at least these kind of problems, centralized configuration, because if you have a distributed system, you don't want to be looking at each one of your artifacts to check which is the current state of your system, because I like to say in the DevOps world, when you deploy things into production and you break things, usually the cause of why did you break things is that you had changes in the things that you run in production. These changes usually comes in three different areas, which are the code, the data, and the environment that you're running. If you're running a distributed system, now you have a different kind of data that you have to handle, because now you have the code that you're deploying into each one of your artifacts, you have the environment, and you have now the state of your environment, because you don't have a single environment anymore. You have the environment, the configuration of each one of your microservices. So that's another variable for you to handle. And you don't want to be, when something goes wrong, you don't want to be digging into each one of the artifacts. What is the value of that variable that is causing this kind of errors? Yeah, you need some sort of centralized configuration for that. Then you also need distributed tracing, because if you had a monolith, you just had a centralized logging, which you just could tail the errors, the stack traces that were happening. But now, since we have a distributed system, you don't have one stack trace, you have many. And you have to be digging, how is this stack tracer related to the other one? If I had 1,000 requests coming per second, how do I relate one error to the other? And worst case, which is, you could even do that manually or centralized logs in some platform, but tracing is so important when you have the hardest problem in distributed system, which is not when something is not working. This is the simplest possible scenario for you to debug. The worst possible scenario is when something is low. Where is the thing that is making your system slow? And usually people, when trying to solve this problem, they think that it's random. So let's just start rebooting the endpoints until we find which one is low. It's not the fact, because most of the times sluggishness into distributed systems is caused by emergent behavior, which is usually caused also by deterministic causes. And so we need a way to solve this problem without adding too much overhead for ourselves. Service discovery, I used to have only one endpoint. Now one endpoint has to access many other endpoints. I need some way for one service to discover the other. I also need load balancing, because now I want things to be resilient, so I won't have just one instance of a single service in my environment. I'll have many. And maybe if you're working on premise, everything is on the same data center, everything is on the same cluster in your company, maybe all of them will have the same response time. Maybe the load balancer will be so efficient that all of your endpoints will have the same loads. So when we're talking about load balancing, we have traditionally two different kinds of load balancing. We have server-side load balancing, where you have these strategies that most of us are aware by now, which is round robin or least resources use it, or this kind of thing. But it's based on the server side. And it does a pretty good job if you have all of the resources collocated. But when you have a larger distributed system, a larger microservice architecture, then you start to have the issues, because each one of the clients, they don't have the same internet connection, they don't have the same hops to get the clients, and maybe this server is less loaded than the other ones. But since my network's much better this way, I'll get a response faster from here. So that's when people decide to use client-side load balancing. So the logic responsible for balancing the requests between the servers is not on the server infrastructure anymore, but on the client side. So you have to be checking which one is faster, which one is failing. This one is better, but it fails in 60% of the times. Maybe I want to try this one for me, because that's a particular case for me, because we have different networks connecting each one of the endpoints. So load balancing can be client-side or server-side. And circuit breaker, which is basically the ability, issuing a request to an endpoint, that thing is failing, maybe I should try another endpoint, because I have a lot of different endpoints in my network infrastructure. Or if everything fails, maybe I can have a default or cached or a secure IS architecture in my own microservice for me to read my values. So these are just 5 of the simplest possible problems that we need to resolve when we're talking about distributed systems and microservice architecture. You see, in 2008, Netflix, they didn't have an answer for any of that, so they have to code all of this. So if you think about, usually, if you think that this kind of things to be sold, this kind of low-level thing, I agree. If I'm an enterprise developer, I'm not worried about how does the nodes get discovered from my distributed system? How do I apply tracing? Or how are the circuit breakers being applied in my architecture? Maybe I don't want to be doing that. As enterprise developer, I think we should be dealing with the business logic, which is the thing that really adds value to the users, and we change people's lives for the better in production. But again, Netflix, they didn't have a choice. They have to, their problem, and their architecture used to be like this. Everything is a business logic. There's nothing ready for me to use. I have to deal with everything myself. And if you ever try to use the Netflix stack by hand, and not with some cool abstractions, just like the Spring Cloud OSS provides you for you. If you use this with the Netflix OSS stack by hand, it's very hard to be using. So well, of course, I never saw their code base, but I'm thinking about some pretty nasty code there. You have business logic, and you have like all of this infrastructure logic that you have to handle in 1,000 lines of code that you're trying to read and write, because the code is not that simple and not easy to understand, because you have to deal with everything all at once, because that's their core business, and that's how they solve this kind of problem. But again, we are in 2017, and maybe, for us, maybe something happened in the past 9 years that could ease our job as enterprise developers. Maybe instead of having to deal with all of this stuff on the application layer, we could just be using coding our business logic on top, just as we used to do in the many years that we've been doing that, and we could rely all of the services into the infrastructure layer. At least the ones that can be solved by infrastructure. If you have a piece of software that can solve the problems already for you, why would you code all of the things by yourself? Why would you be mixing the business logic that you have if you have something that can handle that successfully for you? That's just that I believe that we had the discussion when people created relational databases. Yeah, I want to handle that in my code, persistence things, stuff in my code, but now people don't think about that anymore. I just trust relational database, which is basically now considered an infrastructure service. I just want to save my things and to rate my things, and because queuing, optimization, or how they write the stuff, or how they distribute that, how they store it, it's a matter of a relational persistent service. That's their problem, not mine anymore. So we're always evolving, and we're always trying to rise the abstractions so we can be more productive in what we're doing. At least that's the goal. We can't do that all the time, but we're always trying to rise the abstractions so we can do more with less code. And this is maybe what we can achieve today in 2017 with the tools that we have today. Okay? So, but I wanted to show some code too, not just be talking. So what would be the typical code that you would be creating? And of course, I've been using Spring for the past 10 plus years, so I'm a great fan of it too. So why not start with this? So you see, maybe I want to create some kind of service. Is that too small? Here, and I'll create some Higa, dev days, artifacts, and I want to add some cool dependencies to my project. Maybe I want to add web, A2, JPA, REST repositories. I'm on a whole browser. I want config client because I need centralized configuration. I need a way to consume this configuration. Maybe I want also some circuit breaker, so I have to add my Hystrix client. Maybe I want to load balance, client-side load balance the things that I want. Maybe I'll add an Eureka client, Eureka discovery. Maybe I want some tracing, so I have to add some zipkin. And what else? The service discovery, tracing, centralized configuration. Load balancing, what is the other problem? So I think I covered it all, right? Well, just these dependencies. And see what the code, how how we need to handle that in code. And I know how many of you have suffered from this, because I'm, as a developer, I always like to be trying new and different stuff, because I want to be learning everything else. And when I saw all of this wonderful Netflix OSS stack integrated into the Spring Cloud stack, I just decided that I want to use it all. Okay, let's start putting that into my architecture, because it was simply so cool and awesome, especially when you can do everything that you can, just adding an annotation in your project. So if I get here in my code, so maybe I can the presentation mode, and so maybe I can enable, for example, Hextrix. I can enable something, the Discover clients, because I want to be using Eureka. Maybe I want to enable Zipkin. Tracing. I forgot the notation. But you have a lot of different enable options that you can be using today. And if you want to create just a simple REST controller, here the controller. For example, public string. If I create a get mapping, I could be using that, but I also could be using a remote endpoint to get this information. That's where the distributed system starts to add some complications. So maybe I need a REST template. And forgive me, some of the things won't work because I just want to show very quickly. Maybe I want to have something load balanced because I want some client-side load balancing. Maybe I should be using some REST template here. And forgive me, I'll use field injection because I don't want type constructor for now. And I forgot here bean. And maybe I should be using REST templates, so I get for object something. And we'll return a string. Okay. Just that. I'm accessing an endpoint. I want to return a value, and I think now everything is load balancing. And but maybe my other endpoint is not working, so I need a circuit breaker. So if I want to add a circuit breaker, maybe I could create a fallback methods. And I could use just that Hextrix command, fallback. Yeah. And in the first implementations that I used this kind of tech, I found it simply amazing that for the possibility, which you should consider a distributed try and catch, of course you have more than that, but that's just an oversimplification. It was just amazing for me to provide a simple fallback for that. But then you realize that for many endpoints, you don't have a simple get, you have much more business logic. And maybe some people start to add a lot of different requests, just like get, post, put, and delete, all of the methods. And then you have, if you used to have like 4 methods for the request, now you have 4 fallback methods too. And it starts to become, now you have the business logic and the fallback logic that you have to deal with that. If you have a distributed system, a microservice architecture, where you have only one instance of your service running at a time, then if your call to this endpoint fails, it's for sure you won't have another possibility of getting the response. So the only thing that you can do if you have this very simplistic architecture, which is I have one instance of each microservice running into production, I would for sure need a fallback here. But most of the business logic that we have in enterprise applications are not that simple. It's not that easy for me to provide a default value. So that's when things start to get complicated. Well, maybe REST is not as performant as I considered that for production. In fact, when I was writing the book, that's the #1 complaint of people. I thought it was we're just supposed to create a REST endpoint and things would keep running, but it doesn't perform enough. Then second step is that, oh, it's not performant enough, we need to add a cache. So first they add the internal cache, then they add a cache layer between your monolith and your microservice. Then they realized that, oh, we used to do a lot of different joins in my database, and now we need to do joins in memory because my cache is caching the JSON objects that I should be returning. Then you start to think that maybe this kind of architecture is not as good as we thought about. And then, third and last step, then people start to create CQRS architectures using their own old relational database. So that's one of the implications that you have. So this kind of setup is great if you have like single instances of your service in the background. But then I decided, after coding many different Red controllers in my previous job, I just realized that maybe I shouldn't be thinking about doing all of this, which I consider now infrastructure logic, just in my code. Maybe I shouldn't be responsible for adding the logic for adding tracing, load balancing, and everything else inside my code. Maybe we could do that something in an easier way. And for many months or years, there wasn't a response for that. I had to do it. But again, that's the current discussion that we're having in the container orchestration platform world. And for that, I'll get back to the slides to add another discussion with you. How can we simplify the code that we're doing instead of have to mix their business logic with some things that I consider that should be handled by infrastructure these days? So I have to give you another concept. Think about the big picture. And Netflix in 2008, they didn't have container orchestration platforms. We did have containers, but we didn't have the maturity that we have in container world these days. They didn't have platforms for orchestrating these containers in production. So they had to do everything very tied to Amazon. Even all the other tools like Chaos Monkey and everything else was initially very goal-oriented for Amazon. But if you think about how we deploy software these days, many more people they have available for them. Modern software deployment pipelines. Many of them even are provided out of box. So in many different providers, you have software repositories. If you're using container, you have a container registry. You have continuous integration, continuous delivery tools for you to be using in your pipeline. You have tools for packaging your containers, for deploying them, for scaling and everything else. Things that they didn't have almost 10 years ago. So if you think about the big picture, how do you handle your deployments today? Are you still copying them manually through SSH, SCP, or sync to your servers and getting an SSH connection and restarting the servers? Or are you already using containers for you to orchestrate that? If you're using containers, maybe we can handle that kind of stuff differently. The things I'm going to show you now can be handled even without the use of containers, even though containers makes your life much easier if you have to use these tools. So think about first. We used to have a single deployment for running our applications, but now we don't have just one, we have many. So we're not just doing default deployments, which used to stop the servers, stop the users into productions, copy the artifacts, restart, wait for them to warm, and then the users are okay. So it prevented us for deploying more frequently and more safely too. So now most of the teams that have sufficiently advanced deployment scenarios, they are at least already doing canary deployments, which is the kind of thing. So if you're going to deploy something to production, you have many different instances of your application running, and you're not going to change all of the versions at once. You're going to change just one instance of your application or your artifacts, and you're going to ask the proxy router to give just some requests. If that's a dumb router, which is an infrastructure router, you ask that 10% of the requests to this guy. If that's a smart router, just like the Zoo, for example, you're going to ask, I want customers from internal customers to go here first. Because if they complain, well, they're employees. Yeah, they have to. They don't get to complain a lot. They're supposed to be testing for us. And you have this proxy, but if you have this kind of deployment, then you can think better of how you handle all of this stuff that I showed today, centralized configuration, tracing, and everything else. Maybe we can do something different. And of course, I have to tell you, my preferred platform for running containers today is Kubernetes. And not just because now I'm a Red Hat employee. It used to be before I even joined Red Hat, but now I'm even more excited because all the things that have been evolving in the past months, because they're releasing versions very quickly. So every time I checked what Kubernetes is doing, how the special interest groups are discussing, you have many different features that you can do. So how Kubernetes OpenShift can help me to solve that distributed system problems using infrastructure instead of have me require me to code these things in my application. So first, some concepts. Usually, when we think about deployment, again, I'm talking about container. If I say container, you can consider that to be an instance of your application. Containers will make the distribution, and scaling, and deploying of your artifacts much easier, but you don't have to use containers for that. I'm just saying that your life will be much easier, and you won't have to be doing that by yourself. Again, if there are some things that infrastructure could be doing for us, why don't we choose it? So if you have one container, traditionally you have your container, one container, one instance of your application, but then Kubernetes brought us the concept of a pod. And it was very weird for me because I didn't understand why they called that a pod. I thought the pod was like a capsule. But then that's a problem if you're a non-native English speaker. Then one native English speaker told me that the pod in English is the collective of whales. Then everything makes sense. Because what is a pod? Pod is when you have one or more containers running on the same thing. So when to Kubernetes, it doesn't scale containers. It doesn't run containers. It runs pods. And pods are one or more containers that are running on the same thing. They all run on the same host, so they have local networking. They all have the same life cycle. If one container dies, the pod is killed and everything restarted again. So a pod is a set of containers that have the same life cycle, which means that one container doesn't make sense to have one running without the other. And we have some very interesting scenarios for doing that. So pod containers have the same life cycle. They are very performant because they're all on the same host. They're accessing the same disk. They can connect through localhost, or depending on how you configure, you can even communicate through the same sockets. So that's some of the reasons for you to be collocating your pods, your containers on the same pod. Then again, if you think about the concept, if you have a container orchestration platform, you won't have just one host, because one host is not enough. You have more than one, probably more than 3, because if one fails, all of your load can be automatically scheduled to run on the other containers. So traditionally, if you have your host, we'll have one or more pods running on the same time, okay? And that's what we call pod scheduling in the Kubernetes world. And we have a special set of pods that we can run on the host, which are daemon sets. Daemon sets are a special case of container because if I'm running my application here, I can say I want 3 instances of my application, which is configured in a pod, to be running on this host. Or even I can determine that I don't want on this host. I just want it to be distributed, and based on the load, Kubernetes will decide that, oh, maybe it's better for your application to have 3 instances running here and just 2 on the other node or the other host of your cluster. Then you have a special sets of pods, which are called daemon sets, that you only have 1 instance of them running on each one of hosts. Why is that important? Because now the current discussion that we have today is, in the Kubernetes world, is how some very nice tools, which are called, I'll just name some of them, which are being developed and used for its application. You have, for example, Linkr, which is a project contributed by Spotify to the open source community, which they use to handle these problems that I've just told you today. They solved all of these problems, and they're running containers on the infrastructure side to handle load balancing, circuit breaking, service discovery, and everything else. They're using that to solve their problems. And we have other things. We have, for example, Envoy, which was provided by Lyft, and they released that as open source software because they solved these problems: circuit breaking, load balancing, client-side load balancing, server-side load balancing, etc., etc. They solved the problem, and they are running that as sidecar containers so they don't have to be dealing with that the code. Then we have other projects, Istio, which is they've taken the source code from Lyft Envoy. IBM now is contributing to Istio, and now Istio is an improved version of Lyft. And we have many other projects that are just happening to be appearing every week on the container world, because people realize, well, maybe we don't have to be coding and solving these problems in our applications. Maybe infrastructure can handle that. And for many scenarios, infrastructure can handle this scenario better than code. Which scenarios are that? So I decided in the just very few minutes that I have now, I want to show something running for you. I chose to show you Linkr. Okay, well, Linkr is running, but of course they're just containers, they don't have an interface. I just want to show you which is the result of Linkr running on a system. So imagine Linkr can be configured on your Kubernetes cluster both as a sidecar container. I have my application and one instance of Linkr running here. What does Linkr do? It proxies all of the connections from your applications to the outside, both inbound and outbound connections. Okay? So if you have here, if I request, I want a connection to that service, Linkr will just intercept my requests and decide by himself which is the fastest endpoint available for that. I don't have to change my code. My code just asks for a name, which is resolved by Kubernetes services, which is, okay, it's an oversimplification again, but think about DNS. But the problem with the Kubernetes load balancing is that server-side load balancing. You can add round robin, etc., but if you want client-side load balancing, Kubernetes can't help you. That's where Linkr fits. So Linkr proxies all of your requests, and you can see it's already checking which endpoint is the fastest one. So it's already routing to the faster one. So Linkr does the client-side load balance for you, and it also does the circuit breaking. So if I have many instances, I'm requesting this endpoint. He proxies the connection and asks, well, let's try this one. This one failed. It didn't reply for me or return a 500 error. Linkr, without your application knowing, Linkr tried to connect. Oh, it failed. It automatically checks which is the next available service and routes the request. Your application doesn't even know that your endpoints failed because Linkr is handling that for you. Okay, so and again, this kind of circuit breaking only works if you have more than one instance of each service running into your deployment. That's why you have to do deployment, canary deployments. That's why you need many different instances running in your cluster, because if you have a single endpoint, if that fails, Linkr has nobody to go to check for a reply. So that's. And again, Linkr is the sidecar container that Spotify is using to scale its infrastructure. And not only, because if you think about Hystrix has some very configurable things that you can use in your application, but Linkr has even more intelligence because it has knowledge about the infrastructure. So it has some even more advanced routing and load balancing options for you to be dealing that. And of course, they were implemented by Spotify on that. So, and again, tracing. Tracing, by default, you have to instrument your application code to know, I'm receiving this request, I'm going to add some headers to my application, and I'm going to forward this request to the other service. So later you can use, for example, Twitter's Zipkin to correlate the request that I had. But if you're proxying both inbound and outbound connections, you can use Linkr to add the tracing information for you so you don't have to be adding and changing your code again. So Linkr can do tracing for you again. Or if you have another open source project, which is some people consider even more advanced than Zipkin, you have, for example, Hokular. You can, in Kubernetes, you can inject a Java agent in your application. It will not only trace the request, but also trace all of the performance things, just like New Relic. It will trace all the things, database connection calls, how many times it get taken to go and get results automatic for you, and we will also inject the trace information for you. So what is happening on these graphs? Here, I'll try to increase the font here. Here I have a cluster running, and one of the instances is configured to be a new version of my service, but this version of the service, it fails in 60% of the requests. So I have 5 different instances of my application running, and one of them is a new version, and this version has 60% of the requests failing. Not only it's failing, it randomly chooses one of the requests to be slow. So it's, well, that's a very good new release of software, right? So how does it impact your infrastructure in general? You should be responsible for only 20% of the requests. If you use a traditional circuit breaking approach, which is the first one, which means I try to connect, it failed, I remove it from the cluster. Okay, this is traditional circuit breaking. And you can see that overall, the availability that I have when using this kind of load balancing for circuit breaking, it's around less than 96%, 95% of availability in my service. Okay, at one point, traditional circuit breaking, try to connect, it failed. I remove that, and in the background, Linkerd will keep trying to check, just like Histrix, we'll try to check, is it alive? Replied, okay. Then how many times does it have to be alive to get back? Then that's so it's very similar in many situations to Linkerd, and at most you can have 96% of availability. But what changes if you start to use other kinds of load balancing and circuit breaker, just like the ones that Spotify implemented on Linkerd? First, they implemented this kind of load balancing circuit breaker, which is the consecutive failures. You only remove somebody from your pool of connections if they failed 5 consecutive requests. So you know that this thing is failing, and you need some, at least like, again, it's configurable, but it could be, I need at least 5 consecutive positive requests to get it back on the cluster. So you can see that the availability for this kind of load balancing increases. Oh, just because I said it just decreased a lot. But usually, the overall availability is very close to 98 or 99%. So you can see the average is very high for that. But if we try to use even more advanced circuit breaking and load balancing strategy, just like success rates, this one established that on the past 20 connections to any endpoint, 90% of the requests have to be returned successfully within the response time that are required for that instance to be considered on the cluster. And that's the one that Spotify uses in production. And for that, you can see that the average for the service is very, very close to 99%, and sometimes more than 99%. Because Spotify believes that's impossible, and they're right in this point. It is impossible to have 100% availability. But, and well, even if somebody happens to be on the 1% side, what do they miss? They have to hit play again? Well, I don't know. And that's a service, that's availability rate that Spotify tries to have when they're running. And if you just want to compare how they are working, this is the overtime graphic, and you can see that the orange one, right? Which is the success rate load balancing circuit breaking strategy, on overall is the best performant one. While the traditional circuit breaking, it's between 94, 95%, below 95% of success. The consecutive failures, it's like running between, it can be 96, 99, almost 100, but the best general strategy for Linkerd is to use the success rate strategy for load balance and circuit breaker, because on average it gives you the best performance. Okay, and I'm just showing you circuit breaking and load balancing. Why? Because that's the things that are getting discussed now. Centralized configuration, Kubernetes already has for you. Both Linkerd, Istio, and Envoy, they connect with the Kubernetes API. So you have service discovery already on the Kubernetes platform. You don't have to code that. But the other aspects that I said, circuit breaking, load balancing, and tracing, they're all handled by either sidecar containers, one copy of Linkr running into each one of your application instances. But the thing that some people complain about Linkr is that it's written in Scala. I don't know if anybody likes Scala here. But the problem with Scala is that it has some memory consumption issues. So people that are using Linkr in production, they try to use Linkr as daemon sets. So you have only one instance of Linkr running into each one of your hosts, and it proxies all of the requests incoming and outgoing from your current host. So all of the application instance here already goes through Linkr. And I'm just showing you a Grafana graphs from Linkr, but if you try to use Grafana to graph ICO or Envoy, they all give almost the same results. They have differences between how they circuit break or how they load balance, but the key thing is that we believe that, and that's the thing that is being discussed actively on the Kubernetes community, one of them will be the overall winner, one of them is going to be built inside Kubernetes, but if you don't have to wait for that to happen inside the Kubernetes platform, many companies are already using this kind of sidecar containers or daemon sets to be resolving these problems for you, so you don't have to code all of this in your application. Okay? And, oops. And that's what I wanted to show you today. Of course, I invite you to join developers.redhat.com to download the book or to follow the content, because I'll be writing some articles about the subject on the next month too. Feedback is always welcome. The easiest way to reach me is at my Twitter @Yanaga. And thank you very much.